Okay, I guess maybe we should start.
Okay, yeah, I'm ready whenever.
Welcome everyone to the Quantum Space-Time Seminar. Today we are very happy to have David Meltzer from Caltech, and he will tell us about AdS CFT unitarity and the inversion formula. Let me also remind everyone that the recordings of the talk will be made available on qst.theory.tifr.res.in. This link is mentioned in the email. And in addition to the past lectures, it will also have the schedule of the upcoming talks. So with that out of the way, over to you, David.
Okay, right. So thank you very much for the invitation. I'll be discussing some recent work on AdS CFT unitarity, and this is based on a paper which came out last year with Eric Perlmutter and Alex Sivaramakrishnan, and also a paper which I can hopefully say will come out this month, also with Alec. So broadly speaking, this work is a part of the Bootstrap program, where we try to fix observables by imposing physical consistency conditions like unitarity, causality, and locality. And a very famous and successful realization of this idea is the higher dimensional bootstrap, where there's been a lot of progress just by solving these crossing equations. So in the past 10 years, we've learned a lot about higher dimensional CFTs. So we now have very precise numerical predictions for known CFTs, like the 3D Ising model. And there's also been a lot of progress on solving these bootstrap conditions analytically by studying the inversion formula. So the motivation for this work is we'd also like to understand how to bootstrap AdS CFT. There's some very ambitious questions we can ask are, what is the space of holographic CFTs? And is it possible to show that the AdS theory is necessarily described by Einstein gravity or string theory? So in this talk, I'm just going to focus really on the first question and the general problem of developing a holographic bootstrap. And I think it's useful to distinguish that there's really two different kinds of bootstraps you can study. So the first one is the non-perturbative bootstrap. And this requires that the structure of observables are understood at finite coupling, and that you also have a well-motivated set of axioms for your theory. So here are success stories of CFT bootstrap because we have very rigid structures like the state operator correspondence and the OPE. But the other kind of bootstrap is the perturbative one. And this leverages simplifications that happen at weak coupling. So here a success story is the modern amplitudes program, where people can make progress because we know a lot about the structure of tree level and one loop amplitudes. So for example, at tree level, our amplitude is just this rational function where the poles correspond to particle exchange and a polynomial corresponding to contact terms. And then in between these two bootstraps, I think sits AdS CFT. So we know from the holographic duality that gravity and AdS can be studied through its CFT dual, which has all this nice rigid structure. And we also know that perturbation theory in AdS can be simplified to an on-shell analysis. And this is in line with what's been done in the modern amplitudes program. So ideally, we can try and combine the best of both worlds in the study of general holographic amplitudes. And to be precise, when I talk about holographic amplitudes, of course, all I'm referring to are the correlation functions for the boundary CFT. So these are the natural asymptotic observables if you're an observer in AdS. So a few things we like to understand about these holographic correlators is first, if we assume the existence of a local bulk dual, what constraints can we derive on these correlators? So there's a classic question about how does a CFT know about bulk locality? A more challenging question is, are there any hidden symmetries in these holographic correlators? It's very well known in the study of amplitudes that there can be symmetries in your theory which aren't manifest at the level of your Lagrangian. And there might be, we expect that there's similar things happening in AdS CFT. So these first two questions, I'm really assuming the existence of a bulk dual, and I'm getting properties that my CFT correlator has to satisfy. And then with the third question, we try to go in the reverse direction. And we like to understand what are the minimal conditions we have to impose on our CFT to have a local bulk dual. And these questions, I think, have been very well studied in the past 10 years at tree level, and we have a variety of conditions we impose in our CFT, like large gen factorization and gaps in our single trace sector. But there's been less exploration at tree level, at loop level. So in this talk, I want to focus on studying this first question for one loop correlators as a prerequisite before we get to the more complicated questions about hidden symmetries and the emergence of bulk locality. So to get some intuition for what we should expect about these correlators, it's always useful to think about the flat space limit. So this is a high energy scattering experiment in AdS that lets you reproduce a flat space S matrix element. So somehow the higher dimensional S matrix is hiding inside your d-dimensional correlator. And then there's some natural questions we can ask, like how do the properties of the flat space S matrix, things like factorization and analyticity, emerge from the AdS correlator? And can we go further and show how these properties are generalized when we include curvature corrections? Is there an analog of factorization and analyticity directly in AdS? And in the past few years, there's also been similar questions asked in the context of the sitter and inflationary correlators, especially with some nice recent work on the cosmological bootstrap. But for the most part, these questions have been studied at the level of 4-point functions and at tree level. And if we want to understand the structure of either DS or AdS correlators beyond that, I think we need to introduce some more technology to get a handle on any loop calculations. So in this talk, what I'll be discussing is how to import the classic flat space cutting rules to AdS. And this gives a general bulk AdS unitarity method to compute loop level Witten diagrams. And for simplicity, I'm going to focus just on real scalar quantum field theories in AdS, but everything I say can be generalized to the study of gauge theory or gravity. And of course, ideally string theory. And to prove these rules, it's going to be crucial that we work in Lorentzian signature. So I'm going to make use out of things like out-of-time ordered correlators, causality, and positive energy conditions on the CFT states. But before getting to that, I think it's useful to first review flat space unitarity. And of course, I should say, please interrupt me if there's anything I'm saying that's not clear or you have any questions. So flat space unitarity, we all know, buys us a loop order. If I impose that my S matrix is unitary, I can show that the imaginary piece of my matrix T, which contains all the non-trivial information, is fixed in terms of lower loop data. And this method becomes especially powerful when we have a dispersion relation. So if we can reconstruct it. So that is if we can reconstruct our amplitude from its imaginary part. So in flat space, to write down a dispersion relation, you just do some simple complex analysis. You write your amplitude m as a contour integral in the complex t-plane, and then you blow up your contour, and assuming you can drop the arcs at infinity, you just pick up the discontinuities along the real axis. So what you find is that the full amplitude is fixed in terms of its discontinuity, which is in turn fixed by lower loop data. So for most of this talk, I'm going to assume we can drop polynomial ambiguities. But of course, it's an important problem in both flat space and in AdS to keep track of these terms. But assuming we can ignore them, then we just need to compute this discontinuity. And in perturbation theory, we do this by studying the Kutkowski rules.
David?
So this is something we all learn from Peskin and Schroeder. So we take our diagram and we cut it.
A quick question.
The cuts determine which states are being exchanged in a given channel. And the cut lines are put on shell, and so this trivializes an integral. And what you find is that your cut one loop diagram just becomes a product of tree graphs, which are glued together with the phase-space integral.
Hi, David, can you
And
hear
we
me?
like to understand what's the AdS CFT generalization of dispersion plus cutting.
Hello, David.
And the first part was answered by Karen Vogt, where he showed that in CFTs, instead of studying this object, we should study a double commutator. And we get this by taking an S-channel double discontinuity of our CFT 4-point function. So what he showed is that there's a dispersion formula that lets, sorry, something?
Yeah, I think there is a question, and somehow probably you are not able to hear the audience very well. I also tried to.
Let me turn off. I think it's my headphones. Sorry. Can you try again?
Go ahead, Shiraz. Hello.
Hi, David. Sorry, can you hear?
Yeah, I can hear. Sorry, I have bad headphones, so
No.
I can't.
I'm sorry. A quick question about the dispersion relations in flat space. You talked about how we could reconstruct the scattering amplitude, knowing the singularities of the flat space amplitude, and those came from unitarity. Is there a theorem saying that there are no singularities away from the real axis that are not determined by unitarity?
No, and so that's a problem with dispersion relations in flat space, is that we don't know all the singularities. And so another problem is anomalous thresholds. And so these are singularities in the complex T-plane, which don't correspond to any unitarity cut. And so they appear as an extra term in your dispersion relation. So this is an example where I think in CFTs we have more control because we know all the singularities that can appear. This dispersion relation is rigorous. It's more rigorous than in flat space.
Thank you.
Yep, no problem. Right. Yeah, so this is, I should emphasize that. I mean, Karen Wilson dispersion formula, it's very nice because it just relies on some very basic properties, and with CFTs, we can prove things often better than we can in flat space. On a practical level for us, what's nice about this dispersion formula is that the double discontinuity of a Witten diagram is simpler to compute than the full object. But I want to emphasize also that this dispersion formula holds for all CFTs. So reconstructing the full correlator from its d-disk is really a non-perturbative unitarity method, and it works at also at weak coupling and finite coupling. But for AdS CFT, the missing ingredients are the Kutkowski rules. So we want a way of cutting our box diagram so that it factorizes in terms of two on-shell tree diagrams. And this will make manifest bulk locality, that discontinuities of wooden diagrams factorize in terms of subdiagrams. And then, of course, we can take our sum over cut diagrams and plug them into the CFT dispersion formula to reconstruct the full correlator.
Sorry, by cutting rules, do you mean finding the d-disk of a Witten diagram?
Yeah, so the cutting rules, I want a set of cutting rules for the d-disk. That's
in terms of
yeah.
simpler data, yes. In terms of sort of like on-shell 3-point data.
Yeah, we want on-shell AdS diagrams, or we want some legs on-shell, and we just have a diagrammatic way to compute the d-disk.
Thank you.
And this is good because this brings me to the next point, which is there are really 3 different AdS unitarity methods to compute this double commutator. So the original method is the boundary one.
Hello, David. Yeah, sorry. Just you know, like a side question. So, do you know, like, whether we know how this thing generalizes beyond 4-point functions? Like, we know the cutting rules for higher point, like S matrix, right? I mean, but we don't. At least I don't know whether there's some understanding on how it generalizes to, let's say, 6-point or higher.
Yeah, yeah, that's a good question. So in flat space, it's difficult trying to go through like the old amplitudes literature. I think dispersion relations in the past were very often studied at 2 and 3 points, and 4 points is the highest they studied. I think it is possible to derive. It's possible to derive higher point dispersion formulas that aren't covariant. So you pick out a time direction and you have an energy dispersion formula. And there's ways of turning like non-covariant dispersion formulas into covariant ones, but I don't think people really looked at it that much.
Mm-hmm. So if I understood your answer, like you're saying, even the dispersion relations are not quite understood in higher point, though the Katkowski rules themselves are of course understood. Right? I mean, we can always cut things.
Yeah, I think there are dispersion formulas for higher points. I do think that carries over. I just think I don't know the literature well enough to know everything, but I think those are just more complicated and they were studied less. But in principle, I think there are higher point dispersion formulas.
But what about the analog in CFTs, the analog of you know, this double discontinuity kind of statement by Karan Hua?
Yeah. So I won't discuss that today, but I think no one. So I should say no one has, I think, had any success with that, or there isn't any. There's no successful proposal right now. There are some ideas, and I think there's ways of writing dispersion formulas for higher point Witten diagrams, but it's definitely not understood. There's actually, this is off topic, but there is a question even about dispersion formulas for 2 and 3 point Witten diagrams. And we don't usually think about that because in CFTs, we 2 and 3 point functions are fixed. But in principle, this is something we should also study. So in CFTs, and in AdS CFT, it's only the 4-point dispersion formula that's known, but I think it's generalizable.
Thank you.
You're welcome. Right, okay, so right, with this boundary method, so this was the original method to go to one loop. And the idea is, if I give you a double commutator, you can just insert a complete set of states, and then you get a sum over 3-point functions, and you can try to fix these from crossing and large N factorization. And there's been a lot of success in this program in the study of N equals 4 Braying Mills, and also recently the 62,0 theory. The second method is Euclidean bulk approach. So this is a bulk method to compute the same 3-point functions. And here we can talk about on-shell conditions. but they're imposed in CFT spectral space. So we're putting some conditions in the space of dimensions and spins. And the final method, which I think will be the most familiar, is the Lorentzian bulk one. And here we express our double commutator as a sum over cut diagrams. And this involves a combination of AdS Weidmann functions and CFT momentum space. So we have three different methods, and I don't have time to do justice to them all and how they're all related. So in order of details given, the focus today is going to be on Lorentzian bulk methods. And in decreasing order of details, I'll also mention the boundary CFT method and Euclidean bulk one. But hopefully I'll get the main picture across for all three. So I'm going to start by explaining the CFT generalization of the optical theorem. This is an identity that holds in all CFTs, and it relates the real part of the correlator to the double commutator. Then I'll explain how to derive the Witkowski rules with this identity and show that we get the expected properties that are cuts factorized diagrams into on-shell subdiagrams. And finally, I'll end by explaining the map from both Witten diagrams to the boundary OPE. And this relies on the boundary CFT and Euclidean bulk method. So about this CFT optical theorem, what we want is we want a generalization of this condition on the S matrix. And I'll claim that the generalization is this following combinatoric identity relating different partially time-ordered correlators. So here pi is just the set of partitions of 1 to n into two sets of size r and n minus r. And it's straightforward to check this identity if you expand the time ordering symbol and the anti-time ordering symbol in theta functions and check that they all cancel. So this identity was used in a nice series of papers by Gilwal, Liu, and Ludi to study CFTs in momentum space. And the simplest version is n equals 2. And it tells you that the real part of your time-ordered correlator is fixed in terms of these unordered Weidmann functions. And you can think about this as a simplest unitarity condition. It tells you that the real part of your correlator is fixed in terms of the on-shell Weidmann functions. But here we're really interested in 4-point functions. And there the identity becomes a little more complicated. So now I have these terms where I pair off operators in a time ordering symbol and an anti-time ordering symbol. And I also have terms where a single operator is acting on the left or right vacuum.
Sorry, David, I missed how you got the real part from the previous equation.
I was very quick. So it's, I set r equals 0, and then they're all time ordered. Or I set r equals n, again, they're all anti-time ordered. And so I'm just taking their sum and calling that the real parts. And then for odd point functions, it's the imaginary parts. So it's just a nuisance about studying correlation functions. We're studying amplitudes. Is you have to worry about these factors of -1. So at 4 points, we have this identity for the real part of the time-ordered correlator.
Sorry, Dave. For your identity, is it important that you're in momentum space?
No, I wrote in momentum space because I'll be working in that space, but it's really a position space identity.
Thank you.
It's more useful in momentum space, though.
Would you also talk about the...
Sorry, say again?
Would you also talk about how you got this identity? How one gets this identity?
I wasn't going to, but I mean, this one is a simple one to check. You just have to, I get the time ordering symbols. Let's think in position space. Then this one I get 5x1, 5x2, and I have, you can just, I mean, it's just, you can check that you're taking a sum of two theta functions, like theta t1 minus t2 plus theta t2 minus t1, and that's 1, and so you get like a single Weidmann function. it's not a very illuminating analysis.
Yeah. I mean, more the more general identity with a bunch of five.
This one?
Yeah.
I mean, you have to just prove it by induction. But it's the same kind of thing. It's just you expand this in terms of time ordering symbols, you expand this in terms of theta functions, and you have to check. I mean, you prove it by induction, but the base case is n equals 2, and you check that the theta functions add to 1, and then you do the inductive step.
I was just wondering if there's some intuition that could give some insight into this.
Yeah, so I'll get to some intuition. So I think that would be the next slide, but there's some old textbooks. I didn't give it as a reference, but people use this identity to like prove unitarity of the S matrix. So I can get to some intuition now, which is you can think about this term where I pair off operators between a time ordering symbol and an anti-time ordering symbol. It just corresponds to a 2-to-2 cut. I can insert a complete set of states between my two operators. So that corresponds to this kind of cut where I pair off the external points.
Your identity is true even for a quantum field theory, right? Not necessarily conformal field theory.
Yes, that's true. This is a very general identity. It holds for general quantum field theories.
Hello.
Yeah.
Yeah. So David. So just one comment and one question. So I think the comment is that I mean this is analog of the largest time equation in some sense.
Right.
I mean and the way at least you prove it in S matrix is like how it is described in, let's say, Weltman's textbook on diagrammatics. Which
You're
is
getting like 20 slides ahead of me, but yes.
Oh, sorry.
No, it's good. It's good. It's great.
Just a comment. and the question about this reference. So sorry, I'm not familiar with this paper. So roughly, when was this paper? What is this reference about Gilia's Lulu? Can you tell what was the paper? When was it about?
It was a few years ago. I mean, they published 3 papers. Maybe Gilwell has a series of papers on momentum space and CFTs, but they tried to they wrote a few papers where they tried to they derived some rules for anomalies in CFTs. Mm-hmm. So at 4 points there was this relation. We had the real parts, and the real part only gets a contribution from let's say it's like the A or C anomaly for the TTT 3-point function. And then the right-hand side, they reduced to a single term, which was positive. And so they derived positive sum rules for I forget which anomaly. I think it was CT, the normal distress tensor. But
I think
yeah.
this is enough for me to Google. Okay, thank you.
Yeah, I can also. I'd be happy to send references after. But yeah, so the intuition here is just this piece corresponds to a 2-to-2 cut, and then this piece corresponds to a 1-to-3 cut. So this kind of cut is somewhat of a nuisance. It doesn't factorize our diagram nicely. The only state that's being exchanged can be phi itself. So if we want to get something that looks like a CFT optical theorem and that's useful, we want to project out this cut. And we do that by taking all our momenta to be space-like. So if
just to
yes.
make sure, these are all one loop cut you want to, these are all one loop cut, right?
Sorry, this is not I should have that. This is not a Feynman diagram or a Witten diagram. This is just a representation for the full correlator. And this is, it's not even it's more general than CFTs. It's just a general QFT identity.
Yeah, but sorry, maybe very naive question. So in that case, if I get the intuition from Feynman loop, although these are not Feynman loop, as you said, there can be 2 to 4 many non-trivial things. Those kind of things, they don't play here anything, right?
Oh, when I say 2 to 2, I guess that's not the best notation. I'm just talking about how the operators are split up. Sorry, that's not a good notation. That's my fault. There's definitely others. You could have multi-particle cuts. This is just about like S versus T versus U channel versus
Okay.
N. Yeah, that's all this is. In hindsight, yeah, this is confusing notation. But anyway, so we want to get rid of these cuts. And we do that by taking our momenta to be space-like. So then the real part is just a sum of all these S and T and U channel cuts. And to prove the fact that these 1 to 3 cuts go away, we just use positivity of the spectrum. If 5K acts on a vacuum, this is 0 if K is not in the forward light cone. So here I'm working with a mostly plus metric. So K squared less than 0. But we actually want to go a little further, and we want a way of just isolating a single channel. So we want to find the...
David, quick
yes?
question. If just following up on Loga's comment, your identity applied to a general quantum field theory, and then going on shell literally reduced to Kutkowski's rules, right?
Yeah, yes.
And it was the going on shell part that removed your 1 to 3 cut in a normal quantum field theory. Because one particle on shell.
Well, we don't cut the external lines. I think these cuts can appear in amplitudes. It depends on, I think, the mass of the external particle.
Right. So suppose we had all particles being equal mass.
Oh, then maybe not. But here the external lines aren't really on shell. They're really off shell, which is why
Exactly.
the cuts.
That was really my question. I was wondering whether somehow you're going to K squared space-like was mimicking some of the features of going on shell for an SB6.
You're right. So it's what it's mimicking. It's mimicking amputating the diagram.
Right. Exactly.
So that's what it is. So amplitudes we always amputate, and then we don't have to worry about external cuts. And it's kind of trivial in flat space anyway. These like external cuts are trivial, but yeah, going off shell is like amputating the diagram.
Thank you.
You're welcome. So I want to push this analogy further, and I want to get something like the S channel discontinuity. So what I'll do is I'll just go to a special configuration where all these four momenta are space-like, but the sum of K1 plus K2 is in a forward light cone, but the other sums like K1 plus K3 and K1 plus K4 are all space-like. So in this way, I'm only putting the S channel on shell. So now my identity is very simple. The real part is expressed in terms of just this partially time-ordered correlator. And here I use the positivity condition that if I have a pair of time-ordered operators acting in the vacuum, this is 0 if their sum is not in the forward light cone. So now this identity looks more like the...
Sorry,
yeah.
Can you just explain that? Why is that true? Maybe this last statement.
I think the simplest argument is in a correlation function here, I can insert a complete set of states and they have positive energy. So just for momentum conservation, this is only non-zero if their sum is in the forward light cone. The argument for this argument is simpler because I can imagine H, the Hamiltonian, acting on my operator and this commuted past and okay, yeah, but I think the simplest argument is just a space of states as positive energy, and I can insert a complete set of states.
So somehow the statement is that only annihilators appear in this time-ordered thing. Is that if Ka plus Kj is not in V plus? Is that what I should?
Yeah, so it's just the other time-ordered products. Just vanish when acting on the vacuum.
Okay.
And the intuition is that we're trying to put the S channel on shell. So this is like the same thing in amplitudes, where you take S positive and T negative, and then you're only sensitive to S channel discontinuities. It's just the analog of that, except now all my lines are off shell, and so I have more variables to play with.
Sorry, David, I didn't quite understand why is it that the right-hand side is kind of like an S channel on shell?
It's like when we take like an S channel discontinuity, we're summing over states which can be exchanged in the S channel. Here, the idea is I can insert a complete set of states, and so it's telling me what states are being exchanged when 1, 2 goes to 3, 4. I think that's my intuition, at least.
Okay.
Sorry, David, and just to say again, each of the Ks was space-like, but the sum
Yeah,
of
yeah.
K1 plus K2 was time-like.
Yeah, yeah.
Okay, thank you.
I think I wrote it. Okay, I wrote it in a few equations later. Right, so yeah, I just want to make the point that this looks like the optical theorem. And if you open up old textbooks, this is how some axiomatic people prove unitarity of the S matrix. But here we're interested really in the CFT dispersion formula. So I want a connection to the double commutator. So I'm going to use the spectral condition one more time. And I'm going to show that if all my momenta are space-like, this partially time-ordered correlator is equal to a causal double commutator. So here A and R stand for the advanced and retarded boundary conditions. And in position space, it just means I multiply with theta functions. And to prove this, the simplest thing to do is to take the difference between these two pairs of operators. And again, if you expand things in terms of theta functions, you can show that the difference is the two operators acting directly on the vacuum. So again, this vanishes for space-like momenta. And we can use the same argument to replace the anti-time ordered operators with the advanced commutator. So this is the final result. The real part of a time-ordered correlator is equal to a causal double commutator in these very special kinematics, where everything is space-like and only K1 plus K2 is on shell, or in the forward light cone. And just as a historical note, this equation first appeared in Polyakhov's original 1974 bootstrap paper. And this was 40 years before we knew that the double commutator is a central object in the CFT unitarity method.
How did Polyakov derive or motivate this formula? Or did he just write it down?
I mean, he wrote it down. It's kind of, he was trying to generalize the factorization of flat space amplitudes to CFTs. So he didn't really explain it in his paper. But he gave some arguments, I think the same arguments I was giving for this equality. He just talked about things in terms of creation and annihilation operators. And then to go from this to this, he cited a textbook by Schweber, but he didn't. But that was it. He said it's just standard spectral arguments. And I'll actually get to the motivation in a few slides, but his motivation for studying the double commutator was he wanted some object that factorized nicely. It's hard to explain. He wanted the real piece. He really wanted to study the real piece in momentum space. But to make it look like something with the optical theorem, he had to choose like a very special momenta, and then I couldn't just Fourier transform because that would break all those conditions. So instead, he got it to equal this double commutator in a specific configuration, and then he said, okay, now it's Fourier transform, and now he said this object obeys nice factorization conditions in position space. I don't know I don't know. It's not, reading this paper wasn't clear to me until I read like Yowa's paper, where they explain the same thing in a little more detail.
Thank you.
You're welcome. So the reason we went through all the steps of relating all these different time-ordered or commutators was because we want a way of computing this double commutator. And what's nice about this first line is that there exist standard diagrammatic methods to compute this at weak coupling. And this includes for weakly coupled theories and AdS. So the first line, as was said before, can be computed using Veltman's derivation of the cutting rules through the largest time equation. And the largest time equation is nice because it's a very general identity among Lorentzian propagators, and it can be straightforwardly imported to AdS, as opposed to Kutkowski's argument, which relied more on the specific form of flat space propagators. And the right-hand side, this partially time-ordered correlator, can be computed using the Schwinger-Keldysh formalism. And for those special set of momenta I gave, these two are of course equivalent. But really it's the second line we're after. This causal double commutator is the object that appears in the CFT dispersion formula. And that includes these causal restrictions, which are usually made implicit. But if you look at these two papers where they derive it in position space, you can see that they impose causal restrictions on how you integrate a double commutator. And so it's equivalent to imposing causal restrictions. And so now the idea is, with our special choice of kinematics, we're going to relate the cutting rules for the real piece to the double commutator. And later I'll explain how to relax these conditions. And this is related to the stuff I just mentioned about why Polyakov was interested in the double commutator. So now I can explain or get to the Kutkowski rules in AdS.
Sorry, I didn't ask, which conditions will you relax later, please?
I'll relax the conditions on the external momenta. This space-like and only one is in the color like yeah.
Sorry, David, just to, it's very, very basic. I mean, which side you are thinking of as the imaginary part of T, and which side are you thinking of as T dagger T? Compare, take analogy to the flat space.
Yeah, that's a good question. So it's natural to think of this as the imaginary part, and this is like T dagger T. The double commutator is kind of like the odd man out, where it doesn't have a natural flat space interpretation.
This is the one that enters the dispersion formula.
This is the one that enters the dispersion formula.
I just want to understand the logic.
Yeah. I mean, I can say something that, I mean, very speculatively, it may be for higher point functions or lower point functions. The natural object is really something like this. I'm not really sure. I don't want to. It looks natural, but it's not clear what happens at higher and lower points. What's going to be nice about the double commutator is, well, at this point, it's mostly that it appears in the CFT inversion formula. It's not clear to me. I don't have intuition for why it had to be the double commutator that appeared, but this relation is very suggestive. But I don't have anything concrete.
So in flat space, just conceptually, the program was to fix the imaginary part from the unitarity equation, and then use the dispersion relation to construct the scattering matrix completely, right? Roughly, I mean, in concept that was. So here, how are you viewing various things? What is going
So-
to help you fix?
So yeah, in CFTs, we already have the dispersion formula. The missing piece, I think, as I said before, was just what are the AdS cutting rules? So the goal is to have a new way to compute this double commutator.
Okay.
And as an end result, this is really this is all a generalization of the 60s, really, you know, S matrix, dispersion, Kutkowski, all the 60s technology. But I think the real value in this is it tells us how to go further and what it means. It was never really clear before what it means to cut an AdS diagram. And in modern amplitudes, people do things like max cuts and they do fancier things to fix the amplitude. And so a long-term goal is to understand the same technology in AdS.
Okay, thank you.
Sorry, David, could I just follow up on Abhijit's question?
Yeah.
Just if you just took the first line of your formula, you've determined the imaginary part of the amplitude you want to compute. So would we be able to now you just use complex analysis to say that there is a dispersion relation that determines the full amplitude in terms of the right-hand side of the first part, independent of whether it's equal to the double commutator or not?
Yes, I think that's true. I'm not. What I'm not sure about is there's more than one possible dispersion formula you can write down for CFTs, and the double commutator seems like the nicest. So, but maybe there's other ones, and we can think just in terms of the real piece, and that has nice properties. That could also be the case.
And just a quick follow-up, again, relating to a question Loga asked. The first line here sounds like it will have a simple generalization to 6-point functions, for instance.
Yeah, well.
Right, so why can't we could we just take the point of view that we'll write down the equivalent of that first line for 6-point functions and then use complex analysis to write down some relationship and forget about the analogs of double commutators?
Yeah. I think that's perfectly, I think that this is, I think there's ways of doing that, and some of the stuff was related to like the non-covariant dispersion relations I mentioned in the beginning. I think that's something that's easy to generalize to AdS. But yeah, that definitely seems reasonable to me. Yeah, I think it's a question of like, what's the best dispersion formula? And yeah, that's maybe unclear at higher points.
Okay.
Yeah.
David, perturbatively, how is it that the first equation is buying you a loop level?
Sorry, say that again?
Perturbatively, if you look at the first equation, the flat space unitarity was buying you a loop, one loop order, right? So
Oh, yes.
this one also should do that, do the same presumably. I just want to see how is it doing that.
Yeah. No, that's a good question. So it's I think I'll get to that there's two different ways. One, at this level, it's not obvious until I get to the AdS cutting rules, where I'll show that with this choice of momenta, you can focus on just internal cuts, which factorize your diagram in terms of lower loops.
Okay.
There's another interpretation. What's nice, there's another OPE argument that inserting a complete set of states between like two of these double commutators, the commutators project out stuff that appears at infinite n, or in the free theory, because commutators vanish in free field theory. So that's one argument for this guy. For this guy, you can also make an argument that certain states you insert will vanish for space like external momenta, because it's if you try to insert some states and you compute them by Wick contractions, I think for space like momenta, it would just vanish. And so it tells you that this combination is getting rid of like the free field piece. But I think it'll be more obvious in terms of the cutting rules. Okay. Moving on to now AdS. So now I want to use that identity, which holds for general quantum field theories, but now I want to use it now for holographic CFTs. So in this section, I'm going to work in Lorentzian AdS, where I work in the Poincare patch. So I'll use the standard metric, and I'll be doing a Fourier transform in these flat x mu directions to go to momentum space. So I'm just going to review some basics about AdS CFT propagators. And in a few slides, I'll give their explicit form. But here I just want to use a definition. So in AdS, we have two kinds of propagators for our bulk scalar phi. The first are the bulk to bulk propagators. So I have my usual Feynman propagator, which is equal to a time order 2-point function in free field theory. And I have this on-shell propagator, which is equal to a Whiteman 2-point function. And this is the same definition as in flat space. In flat space, a cut propagator is just a Whiteman 2-point function. And then similarly for my bulk to boundary propagators, they also come in two forms. I just take 1 point to the boundary. So I won't go through the derivation of the cutting rules for the real part, and I'll just present the results here, but if people are interested, I also can explain. I have a few extra slides on the relation to the largest time equation. But I think it's the same as in flat space, so I'll just read off the rules. So if I give you an AdS diagram and I assume that the momentum is running from left to right, so K1 plus K2 is in a forward light cone, then what you do is for each line you cut, you replace your Feynman propagator with a on-shell propagator. For the left half of the diagram, you use the regular Feynman rules, and for the right half, you use the complex conjugated rules. You need to multiply by -1 for each external point on the right half of your diagram. And finally, use sum of all cuts, which are consistent with momentum conservation. So these are the same as the flat space rules. The only difference in AdS is that we have these two propagators and this third rule about multiplying by -1. And that's just because we're not amputating our diagram. While in amplitudes, we always amputate the external lines.
So in flat space, we replace the propagator by a delta function, right? A delta of p squared plus m squared.
Yeah.
And what exactly is the analog of that in AdS, please?
I'll present it in a few slides, but it does correspond. I mean, the delta function is a Whiteman 2-point function. And so there's a similar thing you can do in AdS where you insert a delta function in some propagator, but it's of course a lot more complicated.
Okay, so it's non-exact, right? So there's the radial momentum part as well, right? It presumably is a delta function in CFT momentum, but something more complicated in the radial momentum part.
Yeah. Sorry. There's nothing imposed on the radial momentum. It's not really I don't think it's I think it's simpler to think in terms of just it's a Whiteman 2-point function.
Okay.
If I worked in global coordinates, it would correspond to just having a delta function for the total energy, but I wouldn't be touching anything about all the angular variables.
Okay, thank you.
So David, this G plus is really a sum of the retarded plus the advanced propagators, right? Isn't that?
Yeah.
Yeah. So
I mean, I always, yeah.
that's the delta function in flat space, but it is whatever is the retarded plus the advanced, I suppose, in AdS.
Yeah, that's exactly right.
Okay.
Yeah, I always like to think in terms of Whiteman functions, but you can rephrase everything in terms of the retarded and the other. So now it's the other basis.
And David, I have a question about this thing that like in the momentum space, like you are considering K1, K2 to be in a sense like incoming particles, thinking about K1 plus K2 in the future light cone.
Yeah.
Otherwise, you have to probably sum up at the other cards also where like K1, K4 is coming in and K2, K4 are going out kind of thing. Those kind of unitary cards you have to also include.
Yeah. And I think I'll say in the next slide, if I work with time like external momenta, there'd be even more cuts I have to worry about, like just cutting through an external line. But here I'm trying to keep things simple, so I just have like the internal S channel cuts.
Okay, thank you.
And sorry, and just to be completely clear, it's probably very stupid, but in what you say that G plus here is an on-shell propagator. What sense do those words apply to retarded plus? In what sense?
Yeah, it's just that they obey the they obey the equations of motion without a source, and that's I'll get to this in a few slides, but it's basically the on-shell bulk to boundary propagators would just be the normalizable bulk modes. So it's a solution to the bulk equations of motion that is finite with the Klein-Gordon norm. So that's a sense in which it's on-shell.
Thank you.
You're welcome.
David?
Yeah.
Cut somehow related to this, what is called the split representation?
You guys are asking all the good questions. Yeah, this is, the split representation is, I'm gonna, and there's a split representation for this on-shell propagator, which will make manifest factorization. It's not exactly the same as the split representation people studied before, okay. Which is for time-ordered correlators, which was something we studied in our paper from last year. Yeah. So the last point I want to make, just to emphasize that this isn't that different from flat space, is that this third rule about multiplying by -1 would also appear if you were studying a flat space correlation function. It's nothing special about AdS, it's just the fact we don't amputate our external lines. All right, so there's a few things I want to get to before getting to the cuts. So the idea now is that once I have the cutting rules for the real part, I go to my favorite kinematics, and that allows me to relate the real piece to my causal double commutator.
Sorry, David, just to clarify something.
Yeah.
I'm familiar with cutting rules in flat space only for on-shell amputated S matrices. But you said there is a very simple generalization of that to off-shell correlators.
Yeah. Okay. So Veltman in his 19, I forget, but I think 73 paper, he explained how to derive the cutting rules directly at the level of the Feynman diagrams. So then it's just some combinatoric identity, so it can also hold for off-shell correlators. I think there's a paper by Radu Roybon where it's not something I studied that much, but people do have unitarity conditions like for form factors in n=4. And it's a paper by Radu Roybon where he studied like generalized unitarity for correlation functions.
Okay, thank you.
You're welcome.
Sorry, if I may just add a comment, sorry for interrupting. I think, so Shiraz, David already mentioned it, but it's also very natural from the Schwinger-Keldysh formalism. This is just a statement that the correlation functions of the difference between the right and the left guys vanish. And that follows from, the underlying unitarity of the Schwinger, of the theory. And that is a general statement about the correlation functions without having to go on shell. Yeah.
Okay, yes, thank you.
Yeah. Yeah, so I'm less familiar with the Schwinger-Keldysh formalism, but it does give a way to derive these cutting rules by drawing a contour of the time fold. Yeah. But yeah, there's a very natural connection even in flat space between Schwinger-Keldysh and the cutting rules. So now the point I want to get to about relating the real piece to the double commutator is I restrict it to this set of momenta, but the double commutator is non-zero for more general kinematics. So if I work with these three independent momenta, it's also non-zero if I take K1 and K4 to be time-like. I don't have to, K1 plus K2 is always in a forward light cone because these two operators are acting on the vacuum. So from the same spectral condition, they have to lie in the forward light cone. So the problem of reconstructing the full double commutator is then just a problem of analytically continuing K1 and K4. And the reason we're doing this is because the CFT dispersion formula relies on the double commutator for generic momenta. So this argument about analytic continuation, I think is simplest if I write my double commutator, which I'll call it a function h, as a Fourier transform in three positions. And so here I'm just going to cite some standard arguments from Streeter, Whiteman, and Haag's textbook. So the idea is from causality, I know that this double commutator is only non-zero if R1 and R2 lie in the forward light cone. And here R is just the total separation between the two pairs. So what we can do is we can give K1 and K4 a time-like imaginary part. So I just make this replacement and I choose my vector eta to lie in the forward light cone. And if I do that, then I find this integral is exponentially damped because R1 and R2 are restricted also to the forward light cone. So this implies that the left-hand side is going to be an analytic function in this combination. And so this is what allows us to analytically continue to general time-like momenta. And the full double commutator for generic real momenta is the boundary value of this analytic function. And this also follows some standard arguments about Laplace transforms for Whiteman functions. So before getting to the actual cut diagrams, I want to give just a brief recap of this whole procedure. So the starting point was the optical theorem, and we used special momenta to relate the real part to the double commutator. Then in that set of momenta, we used the cutting rules to compute the real part, and therefore also this correlator. And finally, we use analyticity in momentum space to relax those initial conditions so we can get the full double commutator for generic momenta. So this was the argument. This was why Polyakov liked the double commutator, is because it was related to the real part, which factorized nicely. But then he could use analyticity to reconstruct the full object and Fourier transform to position space. Yeah, there's a lot of interesting things in that paper. So I'll just say that I think this restriction to space-like momenta and studying the real part isn't necessary in principle, but I think it gives a simple way to study the double commutator. And I think it also makes manifest how these AdS rules are exactly the same as the flat space ones. So now I can get to the diagrams, which will make clear how factorization works.
And just to make sure I've understood, the key thing that allowed the analytic continuation of this double commutator, once you word it in terms of a double commutator, is that the fact that it's written in terms of causal propagators. Is this right?
Sorry, say that again?
It was causality that allowed you to do it. And the fact that these commutators were causal played a key role.
Yeah. It was very important that they were causal.
Yes.
Yeah, so I think that's another reason they're so nice is that we can use, they have the, we can express them as a sum of cut diagrams, and we can also, well, let me get to the cuts first. I think maybe that will make it clearer. So the nice thing about this on-shell propagator is that it only has support in the forward light cone. And so this is useful because we set all our external momenta to be space-like. So that means the following cuts vanish when computing the double commutator. So this cut vanishes because my external momenta are space-like, and so this on-shell propagator just vanishes automatically. This cut vanishes, energy flowing through my cut, but the source here, again, has space-like momenta. So this is the 1 to 3 cut, which I discussed earlier, which we're projecting out. On the other hand, if we study the real piece of the time-ordered correlator with general time-like momenta, these cuts would be non-zero, and we would have to calculate them. So I think this is a surprising result. It tells us that the double commutator has less cuts than the real part, and is really the simpler object to study. And so this is also why dispersion relations in terms of the real part, I don't think have been studied that much. It's because I'd have to compute these kinds of cuts, and these cuts don't factorize my diagram in any nice way. And I can make that a little clearer. So if I make this into a loop, let's see, where'd my, okay, my annotate tool is not, let's see, where's, oh, there it is, okay. I can make this into a loop. Let's make it a 2-loop diagram. And then this cut wouldn't factorize it in any nice way. I would just have something trivial on the left, and I'd have a 2-loop diagram on the right. So the fact that we can get rid of these we can get rid of these external line cuts is what makes the double commutator so nice. And then on a more practical level, we can now look at the form of the actual propagators when we're studying the cutting rules. So in AdS, our bulk-to-bulk propagator in momentum space has the following form. So it's this product of Bessel J functions, which encodes all the radial dependence. And I have my usual propagator. And this integral over P is like an integral over radial momenta. And now putting a line on shell just corresponds to inserting a delta function. And so we can use that to remove the P integral. So my on-shell propagator is just a product of 2 Bessel J functions with some restrictions on the momenta. And the simplest way in practice to see that, well, I guess the simplest thing is to take the discontinuity of this bulk-to-bulk propagator, and you see it produces the usual delta function in terms of k squared plus p squared. And this isn't as nice as in flat space, where the cut propagator was just a delta function. But it does represent a simplification over the full propagator. And this also brings me now to split representation. So I didn't explain this, but each of these Bessel J functions just corresponds to an on-shell bulk-to-boundary propagator. So what we find is that our on-shell bulk-to-bulk propagator is a product of on-shell bulk-to-boundary propagators. And this power of 1 over k you can recognize as just dividing by a CFT 2-point function. So this is telling us that cuts will factorize our loop diagrams into trees with on-shell external legs. So as an example, we can look at a tree level exchange. And this also tells us how to interpret this diagram as summing over exchange states. So if I cut my tree diagram on the right-hand side, I get these two 3-point Witten diagrams where I'm getting these two book to boundary propagators just from the split representation. And so here the undotted lines are my regular Feynman book to boundary propagator. And these correspond to the non-normalizable book modes. And the dotted lines are the on-shell propagator, and these are the normalizable modes. Where here it's normalizable with respect to the Klein-Gordon norm. And the difference between the two is this guy is the Feynman propagator is a Bessel-K function. My Whiteman book to boundary propagator is a Bessel-J function. So these objects have been studied in the past. So these diagrams with normalizable book modes replacing some of my propagators are known as transition amplitudes. And so they correspond to computing the vacuum expectation value for some local operators, but now in some state. So here would be two operators where maybe S out is non-trivial and S in is the vacuum. And so this gives us an interpretation for this diagram. It just corresponds to inserting some states between my pairs of operators, and my integral over the forward light cone is just the phase space integral. And this CFT 2-point function, which was that power of 1 over k I mentioned before, just corresponds to normalizing the exchange states. So that's most of what I want to say about these cutting rules. I just want to end by saying that there's a lot of extensions. So we focused on scalar quantum field theory at 4 points, but the same rules can also be derived for gauge theory. And there, the AdS on-shell propagators will ensure that only physical modes contribute to the cut. And this is the same as in flat space. When we do a cut, we only sum over physical polarizations. As was mentioned before, these identities are very general. So the relation between the real part and the calls of double commutator holds at all couplings. And so I could play the same games at weak coupling and derive identities for the double commutator cutting rules for the regular flat space Feynman diagrams. And they would basically be the same as the usual Kutkowski rules. And as was discussed earlier, these cutting rules can also be extended to endpoint functions. But the missing ingredient is the higher point dispersion formula, where here I mean a dispersion formula like what was studied by Karen Wout. So that's all I want to say about the Lorentzian method. So unless anyone has any more questions, in the remaining time, I've already gone over, but well, it depends on what you guys want. I can either stop here or I can discuss the next section.
You have some time. Go ahead.
How much more time?
How much do you think you would need? 10 minutes or something?
If it would be 20 minutes, I think, if I gave all details, but I could skip some stuff. I can just give the general picture. Okay. I don't want to.
Yeah, that should work.
Okay, I'll try. I'll aim for 10 minutes. So I'll just try to give the picture. And so in the previous section, I explained how to classify allowed cuts using momentum space. But most recent work in AdS CFT is done in position space and uses the OPE because there's nice, position space correlators have a nice analytic structure. So in this section, I just want to give a map from the book Witten diagrams to the actual OPE data and explain a connection to what people have studied in the past few years. I'll very briefly review the CFT basics. So I'll use that in Euclidean space. We always have a convergent OPE. We label our operators by representations of the conformal group. And I'm sure everyone knows that in CFTs, 2 and 3 point functions are fixed in terms of these two sets of numbers. So what we do in the bootstrap is we always take that OPE and we put it into a CFT 4 point function. And this gives us the block expansion, where these blocks sum up the contribution of the primary and all its ascendants. And these variables z and z bar are our favorite conformal cross ratios. So in the study of large N CFTs, we can read off the scaling of our 3 point functions just by knowing the large N scaling for our 4 point function. So at infinite N, our 4 point function factorizes, and the tree level piece is order 1 over N squared. And here N is just some parameter. So this implies that the couplings between single traces and their own double traces is order 1, and the coupling of single traces is order 1 over N. So this is now some more standard AdS CFT dictionary between single traces and one particle states in AdS. Here I just want to emphasize that my double trace operators have this dimension at infinite N, and their anomalous dimensions are suppressed by 1 over N squared. And the last ingredient is we need to understand how the d-disk acts on our 4 point function. So this is where it gets its name. The d-disk corresponds to taking your 4 point function and subtracting off the 2 ways you can analytically continue around z equals 0. And the nice feature about the d-disk is that when you act on a single block, you produce some sine squared factors, which have zeros corresponding to the infinite N double traces. And this was the fact I mentioned before, that when you take a commutator, you're effectively projecting out the free field theory piece.
Sorry, David, in the first formula, the top formula for the d-disk, have the theta functions that make the commutators causal, have they been put in?
No. That's a good point. I don't think they make a difference in position space. Yeah, I don't think they matter in position space. It just matters when you use the inversion formula or the dispersion formula. It's how I integrate this double discontinuity. So it's put into the definition of your integration region.
Okay, so you say that the real d-disk includes the theta functions, and you take that into account in how you use this formula.
Right. Yeah. It's just in Simon's paper, he just wrote down the double commutator, and he wrote a formula in cross ratio space, and it doesn't make the causal restrictions manifest. And then in the paper by Stanford, Whitten, and Simmons-Duffin, they integrated the same double commutator, but now their integration region had some causal restrictions. So it's obscured when you work in cross ratio space.
Okay, thank you.
Right. So these double zeros produced by the double discontinuity, as I said, project at the double traces. And this is the OPE version of projecting out external line cuts. So to explain this, I need the block expansion for my tree level diagram. And now here I should say all the cuts are, you should think of these cuts more as a visual guide right now. So I have 3 cuts. I have my internal cut, which just means I have single trace exchange in the OPE. And I have these external cuts because I have double trace exchange also in the OPE. And so these external cuts are just operators which appear in the OPE expansion of the full diagram, but not its d-disk. There is a map between the language I'm using here about cuts and operator exchanges and the cuts I gave before. But the simplest way to think about this is that the cuts let us read off what operators appear in the OPE. So more explicitly, the contribution from this single particle cut is proportional to my tree level, the 1/n 3-point coupling squared. And the external cuts of my diagram contain new 1/n squared data. Things like corrections to OP coefficients and the anomalous dimensions. And taking the d-disk gets rid of the external cuts because the d-disk of a single block, or the d-disk where I take a derivative with respect to n, vanish. And as a reminder, n and l are just the twist and spin for these double traces. So now we have this picture that the d-disk of my exchange diagram is just a single block. And this can, I think, is intuitively obvious from the picture of cutting. So I take the d-disk of my exchange diagram, it factorizes in terms of 2 3-point functions. So all I do is I take the individual OB coefficients from each of these 3-point functions, and I use that, and I multiply my block with those numbers. And this is again just a motivational picture, and it motivated, I think, the earlier work on AdS unitarity. And we can use this picture to understand what happens at higher loops. So from the previous bulk analysis, we have this picture that the d-disk of the box is a product of two tree diagrams. So from our experience at tree level, what we expect is that the d-disk of this box is fixed in terms of the OP data of each tree graph squared. And to make this more explicit, I need the one loop expansion for my d-disk. So at one loop, my d-disk can involve in most single and double trace operators. So the double traces start at 1/n to the 4th with their tree level anomalous dimensions. And this just comes from the sine squared factor. I can also have one loop correction to single trace exchange, but this corresponds to a single particle cut. So let's ignore that for the moment. I'll come back to this later though. So with this assumption, the one loop d-disk is fixed in terms of just my tree level anomalous dimensions. So now going back to phi cube theory, our starting point is we need to take each of our tree level graphs, and we need to determine how they correct the anomalous dimension. And you can do this just by expanding each one in conformal blocks, and you can read off these numbers. And now the claim is the d-disk for my box diagram is just going to be going to correspond to using the anomalous dimension squared in my block. And I think this is a well-motivated picture, and this was the picture people used in a study of getting AdS loops from the boundary CFT. But now we have bulk ways of doing computations, so we can prove this and also extend this picture to higher loops. So
sorry, David,
yeah.
Did you quite understand how you just got the square times the block from this cutting rule?
I didn't explain how. It's just it's a guess, and the guess comes from this picture. There's a way of proving it, but that was all motivation.
Okay.
And right, so since I'm going over time, I'll introduce a tool that allows you to prove this, but I won't go through the proof itself. So the tool is another split representation. And this is the one that's been used in the past in the study of AdS CFT and recently also DS. So the identity says that my time-ordered bulk-to-bulk propagator, or just my Euclidean bulk-to-bulk propagator, can be written as a product of two bulk-to-boundary propagators, where I integrate over their common boundary point. But I also have this spectral integral, which didn't appear before. And what's useful here is that, well, first I should say these propagators have this funny dimension that corresponds to the Euclidean principal series. But since this isn't a dimension of a local operator, I'll say these lines are off-shell. But you can also note this function P has poles when d over 2 plus I nu is equal to the physical dimension. So I'll call this an on-shell single trace pole. And this is the Euclidean AdS CFT version of putting a line on shell. But it doesn't correspond, at least as far as I understand, to our usual notion of inserting delta functions and using Weidmann functions. So the idea is I can use my split representation for on these two propagators. I get two tree graphs. I plug in the block expansion for each guy. The gluing of blocks is very trivial. And basically, when you do all your work about closing the spectral integrals and finding the piece that contributes to the d-disk, you see there's only one term, and it corresponds to picking out the anomalous dimension squared. So it's a lot of technical work, and I can discuss it maybe after the conclusion if people are interested. But I don't want to go through the details now. So now I just want to end with a picture about how to glue diagrams in general in terms of the OPE data. So in phi cube theory, I have 3 exchange graphs corresponding to S, T, and U channel exchange. And the idea is, since the d-disk depends on the anomalous dimension squared, it's going to glue together different diagrams depending on what anomalous dimensions I multiply. And the picture, which I hope is intuitively clear, even if I haven't proven it, is that we have the following map between bulk cuts and boundary OPE. So on the left-hand side, I've drawn diagrams and some two-particle cuts. And on the right-hand side, I'm giving the OPE data you need to put into the d-disk. So the idea is, here I have 2 anomalous dimensions due to T-channel exchange. So I take my 2 T-channel diagrams, I glue them together horizontally, and I get this cut box. I can do the same for these 2 guys. I glue together my S-channel diagrams, and I get the cut for my 2-loop bubble. And similarly for this vertex correction graph. But the general story here is just using anomalous dimensions in my d-disk corresponds to reconstructing 2 particle cuts. And with the bulk method, we have a precise map. And this was an ingredient that was missing before. And the single particle cuts, which I mentioned earlier, just correspond to 1-loop corrections to my OP coefficients. And the story generalizes to higher loops. You just need some 1-loop anomalous dimensions. Okay, so now let me wrap up. I think that was a little over 10 minutes. But anyway, so the main takeaway is that we now have 2 bulk methods to study Witten diagrams. We have the Lorentzian unitarity method, which directly generalizes Kutkowski rules. And we have the Euclidean method, which makes a connection to the OPE and most of the earlier work done on AdS CFT unitarity. And I think the main takeaway here is that AdS CFT correlators really aren't that different from their flat space counterparts. We use a set of ingredients everyone is familiar with, Schwinger-Keldysh formalism, the largest time equation. We can just recycle all our flat space knowledge into AdS. And I think there needs to be a lot more exploration on the general structure of curved space correlators. So I have a list of questions I think are interesting. One is understand generalized unitarity in AdS. And there's a basis of 1-loop integrals. So everything I said was about, again, the old 60s S matrix bootstrap, now in AdS. So it's natural to now try and import the more modern ingredients and get rid of the usual problems in terms of polynomial ambiguities and anomalous thresholds, and all those problems in the original S matrix bootstrap. I also think it'd be interesting to study other spacetimes like the Sitter or inflationary space and understand the analogous factorization and unitarity conditions. Now for the late time observers. Another very active area of research is the study of melon space correlators because melon space correlators in AdS CFT look like scattering amplitudes. So it'd be natural to try and understand the cutting rules in melon space, and maybe things are simpler there, but it's not currently clear. There's other amplitudology you can ask about, which like double copy, polytopes, and on-chain recursion relations. And there's a growing body of work on this at tree level. And I think this should be explored further at tree level and also at higher loops. And I think a very general question and a motivation for this work is it would be nice to, it's nice to understand the AdS scattering in more detail, because ideally we next want to study scattering of higher spin particles and understanding what are the constraints on stringing scattering. And I think this is also a question where we know very little in AdS, and we can hopefully learn a lot more about holography by going to finite string coupling. So that's all I wanted to say. Thank you for listening. I hope I didn't go too over time.
No. Okay. Let's thank David for a very nice talk. Questions?
Hi, David. Maybe I can start with something completely just silly, I think. Could you go back a few slides to the slide where you had diagrams with the cutting rules, a couple behind this, I think.
Sorry, which slide?
This one, yes.
Oh, this one. Oh, okay, yeah.
No, sorry, one behind this. I'm sorry, so you had three lines of diagrams and the CFT interpretation on the right.
Oh, sorry. This one.
Perfect. Okay, I'm being very stupid here, but I don't understand even intuitively why the cutting of this box diagram gives what you say on the left-hand side, these two trees. I mean, in flat space, if I cut the box, I would be cutting it into something else, right? There would be a left-hand side and a right-hand side, and the left-hand side would be 2 3-point scatterings with 2 dangling ends.
I mean, this is the same picture also appeared with the Kutkowski rules. I mean, it's just the only difference was I drew dotted lines because I had Whiteman propagators or the on-shell propagators.
I see. I suppose my question is, why do your middle lines go off to the boundary?
Why do these cut lines go to the boundary?
Yes.
Oh, there's no reason. That's artistic license. That's how I drew the figures.
I see.
That doesn't have any interpretation.
No, I think Siraj is asking about on the left-hand side, why is the bulk-to-bulk propagator gets replaced by bulk-to-boundary, two bulk-to-boundary things from the Kutkowski's rules point of view. Is that correct?
Yes, that's the question. Yes.
But this was the rule. Why, if I cut this line, I get 2 bulk-to-boundary propagators?
Yes.
Maybe you could use your cursor. Your cursor is not visible.
It's not? Oh, that's not good.
Okay, now it's visible. Yeah. But
sorry. Okay. Sorry. This is this is really just more of a. This is just to explain the connection between the anomalous dimensions and what diagrams like loop together. This is not a precise map. The precise map is going all the way back to the Kutkowski rules. Something like this is the precise map. And yeah. But sorry, let's see if I can. but I can draw the same diagram for a box. So I can imagine. I'll do the same thing, right? I would cut this box, and then it corresponds to this thing. Well, okay, I'm sorry. This is a very bad drawing. It's the same drawing. I'm just maybe these lines would be dotted.
Yeah, but the lines on the right are these G pluses, right?
Yeah, yeah.
And that's not the same as bulk to boundary propagators.
Yeah, so that other picture was just it's not a precise bulk cutting thing. It's just it's like a monomer. It's a way of interpreting it, so it's clear what I'm doing. And this is because that whole section was Euclidean, and so I don't really have the Kutkowski rules. It's just I'm trying to explain. Yeah.
Is the question that why is the cut lines not dangling but taken to the boundary?
Yeah, right, something like that. I knew what the cut lines were. They were these G pluses, the analogs of the delta function.
But I thought cutting is like putting the particle on shell, and then on shell particles are like asymptotic states.
Yeah, so right, so the drawing, if you like, is, let's see, this is really testing my drawing skills. I'm gonna redraw this in a different way. So I can take this cut. I wonder if I can, okay. And this is, you could say this is just equal to a, I'll try to draw a dotted line. Something like this, where now it's supposed to be, this is just an on-shell bulk-to-bulk propagator. So this is what the cutting rules tell me. I just take my bulk-to-bulk propagator and I replace it with this on-shell object. But then what's nice is that from that previous identity, let's see if the drawing stays. Okay, well anyway, from this identity, this bulk-to-bulk on-shell propagator can be expressed as a product of two on-shell bulk-to-boundary propagators. So that's why it becomes two diagrams. Is that clearer, or?
Yeah, that's clear. And the conformal field theory data on the right was just saying that same diagram, that same tree diagram captured that anomalous dimension in conformal field theory.
Yeah, yeah. It's just, sorry, I want to erase this diagram. Yeah, it's a problem where this Euclidean method, it's very nice from the OP point of view, but from the way we usually think about cutting, it's a little strange. So what it was trying to capture was just this equation. The d disk of my box, well, this is not, that's not it. This one, the d disk of my box is determined by the t channel anomalous dimension squared. So it was just trying to capture that equation.
Right, okay.
And now for these, let's say, for these guys, I'll just use different anomalous dimensions in my d disk. But yeah, this is misleading because it's Euclidean, so it's not really a cut.
Any more questions?
Hello.
Yeah.
Yeah. So if I may, like, can I ask, like a somewhat of a slightly meta question, which is that, like this kind of cutting rules and so on, what does it allow me to compute more easily than other methods? Let's say compared to, let's say, million amplitudes or something. Like, is there some? I mean, what is the object which can be in this thing? For example, should I take the answer to that question to be the slide that you have, that, is this anomalous dimensions if we wanted to calculate from the bulk? You think it is easier to compute by these cutting methods than
Yes.
than doing the loop integrals or something?
Yeah, it's a good question. So there's two different methods we have. There's that Lorentzian method and the Euclidean one. So with the Euclidean one, at one loop, I think, so at one loop, people did calculations before, but there was some disagreement in the literature about, there was a bulk Wooden diagram approach to compute something, and there was a boundary CFT approach, and the two actually didn't agree. And there was some confusion about that. And so this method is nice because it explained the deviation. So I'm talking about, this Euclidean method. And then we can also, it's also easier to go to two loops. I think from the problem with the purely boundary approach is that it's hard to tell what to compute. I can put in some anomalous dimensions, but it may not be clear like what I need to put in to get the full two-loop correlator. And so this ladder is a good example of that, because the ladder, of course, also has another cut. It has this cut. So the existence of this cut tells us that we can factorize it in terms of 5-point functions. So I can cut my diagram in two, and I get two diagrams like this. So I'd argue from the purely CFT perspective, it wasn't clear. I mean, we expected from the flat space cutting rules, but it wasn't clear maybe how to get this cut. And so we can compute that with this bulk method. There's also, but melon spaces, you can do like bulk melon space calculations. And so melon space, there's some work by I think Ellis Wan where he studied similar things, but in melon space, and he got some nice results there. For the Lorentzian cutting rules I gave before, there it simplifies some computations. There's some tree calculations which are it's hard to do in full, but you can take the discontinuity and compute it very simply and plug that into a dispersion formula. But I think the real nice feature of the Lorentzian method is it just tells us what it means to cut a diagram, and I don't think people should try to redo the 60s S matrix bootstrap in AdS with the dispersion formulas and the cutting rules. I think people should try and, well, we hope to also try and like understand the basis of one-loop integrals and try to fix amplitudes that way as opposed to direct calculations.
Mm-hmm. For example, do you think that somehow this thing that you mentioned, the generalization to higher loops is easier in this way of thinking about it?
It's definitely easier in the sense that we could, in our paper, we could do this. We could like compute the two-loop ladder. We can compute this cut where it goes into two 5-point diagrams. If you want to do that from the purely CFT bootstrap approach, you need to understand crossing symmetry and the inversion formula for 5-point functions. And that's unknown, and it'd be very interesting, but it's right now it can't be done. And so with this method, we can actually do the computation, and then hopefully we can check in the future against a more CFT analysis.
Okay. Yeah, somewhat of a different question. This is regarding something that you mentioned in your future directions and so on. So it's also somewhat of a meta question. So this is the statement about like inflation and de Sitter in general. So you think that most of the things that you're describing here generalize directly to de Sitter, that and let's say let's say the statements about this cosmological collider physics and that kind of things.
Yeah, so I think that's another interesting application. I think it does generalize to DS. I mean, I'm sure there are people in the audience who know it better than I do, but the calculation of the wave function, the Sitter in inflationary backgrounds is very similar to this. You can get it from analytic continuation of the partition function. So I think yeah, a lot of the tools I described here, I think, can be generalized to inflationary backgrounds. Yeah, there's some nice work in the cosmological bootstrap where people fix like 4-point functions by imposing like an ensemble and imposing consistency conditions. And so these cutting rules would just be I think it's another ingredient. It's another way to try and fix 4-point functions from a purely, in that case, it's a purely boundary perspective. But yeah, so I think it's all generalizable, but yeah, I'm not the expert on inflation.
Okay. Just one last question, and then so regarding these two loop diagrams. So do you understand right that you guys have studied mainly the scalar things? Like, did you look at gravity two loops and so on? The physical question I wanted to ask was, so there's a two-loop non-renormalizability in gravity in flat space, right? This Garoff signality, the non-renormalizability of pure gravity shows up in two loops. And the point is that there is a way of thinking about it from, I mean, you don't really have to compute the two loops. I think you can just look at it from just cutting the two loops and understanding these divergent terms, like this is some work that I think Zwieber and collaborators had there's some way of doing it. Okay, but the question is that whether so and as far as I understand, it is not understood what is a corresponding statement about CFTs and double discontinuity is. So there should be some statement to the extent that if you truncate to just pure stress tensor sector, then there should be some kind of incompleteness, like once you start going to the analog of bulk two loops. But
I mean,
yeah,
the UV divergences from the CFT point of view.
Yeah. So basically, the non-renormalizability, the UV divergences are one thing, but yeah, the statement that there's some non-renormalizability, whatever that is in the. So that is motivation for this question, for asking whether you have looked at gravity too, and whether what you're doing would be useful for that answering that question. Yeah.
So I wasn't aware of that work you mentioned, but that sounds like our work could be useful in understanding the same thing in AdS. Right. So there has been some work on understanding divergences and non-renormalizable theories in AdS. This was done in the first. Let's see if I had the citation. In the Aharoni Aldebisi Perlmutter paper, they related divergences to loop divergences to how these anomalous dimensions grow when I take little n large. And there's some intuition that that limit corresponds to high energy scattering. But there's been less work. There's maybe some papers, I think, by like Ivo Sachs, but there's been less work on studying these UV divergences from a directly AdS perspective. The expectation, though, is that the AdS UV divergences would be the same as in flat space. So I don't know. I think it would probably be the same as whatever they saw in flat space.
Yeah, but I was thinking whether you can make a statement about the double discontinuity in a CFT with just purely stress tensor.
Yeah. So there is a way. It's very technical. It's very difficult, but there is a way of going. There's a way of going to loops purely by solving boundary crossing symmetry, and well, sorry, I didn't think about that. Yeah, if you think about purely from the boundary perspective, it's very easy to get stress tensor exchange. I'm not getting the quartic interaction correct would be a lot more difficult, but that should also be, you should be able to fix that from a purely boundary perspective. Yeah, There is a way you can the boundary CFT point of view is that you just solve your bootstrap equations, you find these anomalous dimensions, and you plug them back in, and then you would see if that thing, if when you use the dispersion formula, if the final result diverges or not. And so you could, and there's ways of checking the derivative order like of the contact term you need. So I think it's possible, but it's something very technically difficult. Yeah.
Okay, thanks.
You're welcome.
Sorry, perhaps this is the question that you just addressed, but you know, when you want to use these unitary methods loop by loop to fix the correlator, presumably at the first step, the polynomial ambiguity involved in this dispersion relation would be fixed by the chaos bound, or it would tell us some constraints on this polynomial ambiguity. But at the next order, do we know what sort of how is the polynomial ambiguity constrained?
Yeah, so that's a good. So the chaos bound is something that's not perturbative, and it tells us how the full correlator grows, and like the Regge limit, where it's like S goes to infinity, and you keep T fixed. But in perturbation theory, at each order in perturbation theory, the divergence the chaos bound is violated in perturbation theory. But at each order in perturbation theory, you get like your polynomial increases by one order.
Sorry, what I mean by the chaos bound is the one that is applicable to the first perturbative correction.
You mean
that it should go that it should not grow faster than S squared in the Regge limit for the first correction.
Yeah, that's at tree level.
The thing should not grow faster than S, right?
Yeah. That's at tree level. The chaos bound tells us, yeah, there's a bound on the polynomial piece. It's like you can have S squared over T, and you can have a linear piece S, but nothing higher.
Right.
Then once you go to higher loops, you can like increase the divergence by one, and so it's always bounded. But
so this is something that that the next constraint is weaker by one order and so on.
I don't know if that's a constraint. It's just it's the expectation from effective field theory, and just you increase the derivative order, and so you get more. The divergence becomes a little stronger. I guess that's. I guess maybe you can prove it. I guess if I know the structure of the tree level theory. But anyway, it just becomes a little more divergent each time. I mean, this is just effective field theory. So yeah, and so that tells you that there's more and more. The usual dispersion method is there's more and more polynomial ambiguities at each order, and you need an independent way to fix them.
Okay. Any more questions? Okay, if not, let's thank David again for a very nice talk.
Yeah, thank you.
Thanks a lot, David. That was really very clear and very nice.
Thank you. Thank you for all the questions. It's good to get questions during the talk.